Hello. What we're going to do is we're going to discuss the solution to linear first order differential equations. And in this video, we're going to explain why a given solution will work. So without further ado, let's get started. Now, first of all, a linear first order differential equation which I'll write. Now, I won't go into that for this video. I won't go into the reasons for the word linear, but that's something that's commonly discussed in differential equations tests. But for our purposes, it will be things of the following form. You'll have the derivative of a function plus, in this case, I'm writing this, you'll have p of x, some function of x, times y equals some function q of x. For example, and I have a few examples written down here of this type, you might have something like, you might have things like y prime plus 1 over xy equals x plus 1 over x. So here the p of x would be 1 over x, q of x would be x plus 1 over x. Or you might have it in slightly different form. You might have something that looks like this. You might have initially, this might not look the same. This is a 1 over x squared. This is not exactly in this form, but if you divide through by x cubed, which means you have to take x equals 0 out of the domain, you'll get y prime plus 2 over x cubed y equals 1 over x cubed e to the 1 over x squared. So in this modified form, your p of x would be 2 over x cubed. Your q of x would be 1 over x cubed e to the 1 over x squared. So those would be examples of that. Now, let's just turn to an example like the first one. Or let's look at this in general. In general, if we have, let's say, y prime plus p of x, y equal q of x, if you notice, there's a y prime here, and you notice that there's just a plain old y here. That's the first thing you notice. That's a point 1. Point 2, from calculus, you know that if you have the derivative of y times some function u, you just looked at the derivative, took the derivative of this. By the product rule, you'd have y prime u of x plus, in this case, u prime of x times y. Now, the reason why this is something nice to have, you know, having the derivative of the product of two things like this. So if we had our differential equation, the derivative of y u of x, y times u of x, so let's just rub that out. So if we had this situation where you had the derivative of the product of two things, so let's get this straight here. If you had this equal to some, let's say, f of x, so if you had that thing, on this part right here is a perfect derivative, meaning it's a derivative of something. You could then integrate both sides. you could then integrate this, and you could then integrate that with respect to x. And if you did that, so if you had a perfect derivative, if you integrate a derivative, you get the function back plus a constant. Then you get this integral of f of x dx. And I'm including the constant integration within this integral. Then your y would be 1 over u of x, integral of f of x dx. And you'd have a nice formula for the solution to the differential equation that looked like this. So that would be nice. So if we looked at, let's say, this thing here, the very first one I wrote, where, you go back to this example where I wrote this as we had this y prime plus 1 over xy, and that was going to equal x plus 1 over x. Now, this is not in this form. This is not in this perfect form here, this perfect integral form. You have y prime and you have y, but this u of x, well, you would need u prime of x here, and you would need, you need u of x here, and you need u prime of x here, and we don't quite have that. But we started this, and then we took, let's say we took this differential equation like this, and obviously I'm doing something like this. And let's say we decided to multiply both sides through by x. Now just indulge me here. So suppose I do that. Then we have xy prime plus y equals x squared plus 1. Now notice what we have here. This is now a perfect derivative because this thing equals d dx of, well, here we have an x and here we have a y. Now, why is that so? Well, by the product rule, the derivative of x is 1 times y, and then the derivative of y is y prime times x. So this is a perfect derivative like there, like so. So what we multiplied by to get a perfect derivative, this is going to be called the integrating factor. And the reason it's an integrating factor is it makes this part right here, the left-hand side, this part right here. So what it makes this, or it makes this into a perfect d dx of something like that. So that's the integrating factor x. So now we can go ahead and integrate both sides with respect to x. The integral of the derivative is just the function. This is now going to be x cubed over 3 plus x plus constant. That's important. Then to solve for y, we just divide. And this is your solution to your differential equation right here. So what we see, what we saw there was the idea that something that wasn't in perfect form, and a differential equation that wasn't in perfect form, could be turned into perfect form by multiplying both sides by a clever choice of function. So that's going to be what we want to do. Now let's go back and look at the original differential equation, the abstract one. So we have y prime plus p of x, y equals q of x. Now, is there anything in general we can multiply both sides by? Can we find an integrating factor to multiply through by so that the left-hand side is a perfect derivative with respect to something equals something times q of x? And the answer will be yes. Now, for those experts here, this is provided provided p of x is continuous. And it's going to be on some domain. So what works? So let's just keep in mind, so what works? Well, if we take y prime plus p of x, y equals q of x, we want to multiply something. And when we want to multiply by something where, and let's just call this thing u. We want to multiply it by some u of x. And what we need is that this thing here is going to equal the derivative of u of x times y to be a perfect derivative. So what this means is that when we take the derivative by the product rule, we'll have u of x times y prime, that's this stuff. But then we need the derivative of u of x has to be itself times p of x. So what in the world can we do? Well, this is what we need right here. We need the derivative of u to be this. It's a differential equation itself. And one of the things we can do is that we can go ahead and solve this by separations of variables. So what I want to do is I'm going to suppress the x. So what we have is du dx is equal to u times p of x. Using the separation of variables technique, we can write du over u equals p of x dx. And I realize that these are not fractions, but what we're really using is we're using the substitution rule. Now we can integrate both sides. And the left-hand side is now log of absolute u is going to be equal some antiderivative. And I'm not going to worry about the constant here. We need something that works. Then what we can do is we can now take e of both sides. E to the log of absolute u is absolute u is now e to the integral of p of x dx. And since this is going to be positive, we just need an antiderivative that works. We let u of x equal e to the integral of p of x dx. And this integrating factor always works. If p is if you can integrate p, that is, if p is a continuous function. So this u that we just discovered here is what we need to multiply by to make this a perfect derivative. So getting back to our original, if you do that, if you multiply both sides by e to the integral p of x, we now have the derivative of e to the integral of p of x dx times y. Now it's a perfect derivative. E to the integral of p of x, q of x, well, let's call that big Q. Changed cases on you. Then integrate both sides. So we can now integrate both sides with respect to x. And what we get after integral of the derivative is e to the integral of p of x dx times y is equal to the integral of e to the integral of p of x q of x dx. And then what we do now, and to finish this up, and we're just about done with it. We only need one more line. Finish up, we just multiply through by this. So we have y is equal to 1 over, and I'm going to write it the way the textbook does, dx, times the integral of e to the integral of p of x, q of x, dx, and then the text calls us u of x. And keeping in mind that when you multiply this thing by u of x, it has to be the whole thing. So when you resolve this integral and you get a plus c, this you multiply that to get the plus c. So let's just go ahead and just do an example. An example I chose, and this is a nice little one here. But suppose we have y prime plus sine of xy times y is equal to e to the cosine x. Now the integrating factor that we said would be e to the integral of sine of x dx, which is e to the minus cosine of x. So now if you multiply through by e to the minus cosine x, you get this. So this part here is 1, and this part here is a perfect derivative. So now when you differentiate, so now this is a perfect derivative. So now when you integrate this, the right-hand integral is pretty easy. It's just going to be x plus c. This integral is the integral of the derivative. So we get e to the minus cosine x times y is equal to that. Then multiplying through both sides by e to the cosine x, we get y is equal to x e to the cosine x plus c e to the minus cosine x. So you can see this works pretty readily. Now, for those of you who are in my class, we will do many examples of this, of solving. But I just wanted to show you why it was true, why this thing was true. So thanks for watching.